My name is Kevin Doyle, and I am the HDSI's Assistant Director of Programs and Operations. It's great to see so many people here today. Before we get started, I want to thank our partners at Esri and Harvard Center for Geographical Analysis for making this workshop possible. Our colleagues at Esri have generously donated their time and talent and have made their ArcGIS software free to the Harvard community. Wendy Guan and her colleagues at CGA have made laptops available, but that's not for today because the university is actually still shut down. So that will be for the next two, and have worked hard to make sure the tools you need are accessible. We are extremely grateful. It's now my pleasure to introduce Lauren Bennett from Esri. Lauren leads the spatial analysis and software development team at Esri, having come to this role after starting her career with the company as a federal solutions engineer in 2007. Lauren received her PhD in Information Systems and Technology from the Claremont Graduate University. For the past several years, Lauren has been a close friend and collaborator of the HDSI, and we are delighted to have her here today. Lauren, you can take it away.
Awesome. Thank you so much, Kevin. And welcome everybody. We are super thrilled to be here today and to have this time with you. Our hope is that it's going to be a really fun, for me, morning, for you, afternoon, and that we'll kind of pique your interest in some of the things that we've been working on and just in spatial analysis in general. And honestly hope that it's the start of a lot more collaborations. We're thrilled with our collaboration with Francesca and HDSI, several of the women on my team, and along with Francesca and some folks from her team, just had an article published in Nature as part of our collaboration, which we are thrilled about, not just because obviously it's Nature, but it was a super important topic about environmental justice and the inequities in air pollution exposure in terms of race, ethnicity, and also socioeconomic status. So really important research that we were thrilled to be able to collaborate on. So this is the first of 3 workshops. I don't want to say this is my favorite one, but it probably is. I feel like I'm not supposed to have favorites like my children, but we all know this. It changes from day to day. But today we're going to talk about cluster analysis and space-time analysis, specifically kind of statistical approaches to that, spatial statistical approaches to this kind of cluster analysis. I would say that I know it's 2 hours of content, and it's that sounds like a long time, but I swear we could talk about this all day long. So we have that extra hour at the end where we're hoping that we'll be able to kind of talk to you about maybe some problems that you're trying to solve, some data that you want to bring to some of these tools and how we might help you be successful, or just kind of have a conversation at the end there. So we're looking forward to that as well. And we've got quite a few folks from our team that have, in addition to the presenters, Lynn and Alberto, so that we can, yeah, you guys can come on in if you want to, Alberto and Lynn. Lynn and Alberto are both product engineers on the spatial statistics team. And I know I speak for all of us when I say we're thrilled to get started. Okay, so the first thing that I want to talk about is, and also one more logistics. I feel like there's a lot of logistics. One is one of the things mentioned on the sites about this workshop series is the competition at the end, where there will be a competition that is being hosted by HDSI around creating a story map around your unique research. And the details about that are going to be emailed out after the 3rd workshop. We don't want folks who participate today to have an extra 2 weeks prep time for that. So for the sake of fairness, those details of that competition will be sent out after the 3rd workshop. So this workshop's about statistical cluster analysis. Next Friday, we'll be talking about some machine learning based approaches to doing spatial clustering. density-based clustering, multivariate clustering, that sort of thing. And then the third week, we're going to be talking about story maps. And so I think one theme you'll see kind of run through here is that, of course, really great analysis is important, but if we're not able to effectively communicate that analysis, then in some ways, kind of what's the point, right? It doesn't matter how great your analysis is. If no one understands it, if no one can figure out how to make use of it to make better decisions, then we're really missing that. It's like that last 10% to go all the way. And we're going to talk a lot about some of the techniques to storytelling and the power of story maps for telling those compelling stories about advanced analytical methods and research. So after that workshop, then those details will be sent out for the competition. I'll also mention that we sent out a link where you have access to the ArcGIS Pro projects that we'll be taking advantage of today in the workshop, and you can follow along as the demos go. You absolutely don't have to. You can watch and you'll still just get just as much out of it. But if you want to follow along, you absolutely can. And that will hopefully help you start to feel like you're getting your hands dirty. And then we can use that last hour to get them even dirtier. Okay, so with that, I want to start with a topic that is very near and dear to my heart. All of our hearts really, but I feel particularly, this is, I guess I would call it my soapbox, and this is about the subjectivity of maps. So the thing about data, and I think we are increasingly seeing this, is that there's a increased acknowledgement, I guess, that there's a difference between data and information, right? Just because you have a lot of data doesn't mean you know much. And there's actually a lot of work that goes into turning data into information.
Lauren, I don't see your screen. I'm sorry to interrupt.
Oh, you don't see my screen. I'm so sorry. Thank you for interrupting. Well, what everybody missed for a little bit, while I didn't realize you couldn't see my screen, was this slide, which doesn't have all that much on it other than the name of the course and our names, and then my soapbox, the subjectivity of maps. And so there is this growing understanding that there is a difference between data and information. And I pose the question, does putting your data on a map turn it into information? And I know that it might seem sacrilegious. We come from a software company that builds kind of the mapping software, for me to say no, but I don't think it does. I don't think just putting your data on a map turns it into information. You know, if I handed you a spreadsheet with 100,000 records, you probably wouldn't feel very comfortable making a decision using that spreadsheet. So if I take 100,000 records and I just plop them down as points on a map, you're probably going to feel maybe a little more confident, possibly more confident than we should by looking at that data on a map. So this is stop and frisk incidents in New York City from 2017 to 2020. It's going to be the topic of our demos today. And you know, there's a lot of issues with stop and frisks, and they get at a lot of equity issues. And one of the things that we wanted to do when we started exploring this data was understand what kind of spatial patterns we could find, and also to understand if there were kind of inequities in the way that these stop and frisks were being performed. Today, we're going to focus on the spatial patterns. We will point you at the end of the workshop today to a learn lesson, like a hands-on learn lesson that just came out today, actually, that gets a lot deeper into exploring this stop and frisk data if you're interested, and it's across different cities too. So we're not just limited to New York City, but today we're going to focus on understanding the spatial patterns. And I think just dropping this data on a map, certainly we start to see, we get a little bit of information. It's kind of like we put one foot in information, but we've still got another foot very square in data. And there's a bunch of issues with this kind of data. With points on a map, one of the biggest issues is coincident points. So if we look here, you know, over here it seems sparse, but for all we know, the way that this data was coded, one of these points could represent a particular intersection, let's say, and actually it could represent 100 points, but because they're in the exact same location, it just looks like one, right? It's just one on top of the other on top of the other, and we can't tell. The other issue is with the amount of density in this data. Is this area in the Bronx denser or less dense than Harlem? Is it denser or less dense than Queens or Brooklyn or the Lower East Side? You know, we really can't tell, because once you reach a certain level of overlapping points, it's just a gray map, right? And it's a blob of points that we can't really interpret. So one of the, I would say, most common ways I see people kind of start to move beyond points on a map is something like a heat map or density surface. And these can be really useful. Immediately we start to see, okay, well, it looks like perhaps the Bronx was the denser area, certainly, than some of the other areas that looked like a lot of overlapping points. So we do start to get a sense of the density in our data, and we start to learn a little bit more about our data. But if I was to ask you to make a decision based on these maps, you know, which one would you choose to use and why? And do they represent the same information? I think that one of the things that is really dangerous about maps in general is that most people have never made a map. And I mean, in the world, and I wish we were in person, because what I would do is I would ask you, how many of you have made a map? And I'd see hands go up, because, you know, usually I'm in a group of people who at least some have made a map. But if I was on the subway and then I asked a subway car full of people, how many people have made a map? Very few people would raise their hand, right? Because it's just not something that most people have done. But most people have interpreted a map, have made decisions based on a map. Most decision makers have made decisions based on maps that they've never made. And that can be really dangerous. And this is why. So what you might know if you're someone who makes a lot of maps, or what you might kind of have a clue about, is that actually these two maps are the exact same data. The only difference is the classification method that we used to symbolize them. So in the map on the left, to be dark red, you had to kind of have a density value of over 550. But in the map on the right, where we used a quantile classification method, to be dark red, all you need is a density value of over 142. So the buckets that we chose to put these the values into to determine what's going to be red on the map and what's going to be blue on the map really change the story that these maps tell. You know, if I was trying to make a case for how big of a problem stop and frisks are in New York City, I might choose the one on the right, because it really makes it seem like it's a massive problem. If I wanted to show that, you know, really stop and frisks are down, they're really not as big a problem as you think they are, I might choose the one on the left, because it looks a lot less severe, right? Or if I wanted to say, actually, they're very equitable, look at the one on the right, red's everywhere. So clearly we are frisking everywhere, right? So we can tell these different stories depending on which map we use. The reality is we don't really want to choose that way, right? We want our map to, as close to as possible, represent reality and help us understand what's really going on. And as map makers, we have a lot of power to tell the story that we want to tell. And people really do think of maps as objective truth. I mean, when someone sees something on a map, it must be true. It's on the map, you know, but the reality is we, as the map maker, had a lot of power in what that map's telling people. And so with great power comes great responsibility, as Spider-Man's uncle famously said. So we have this huge responsibility, and there's a lot that we can do. And this is not, please don't, I absolutely don't mean to say density surfaces aren't useful. I truly believe that they are. We certainly got a lot more information out of that density surface than we did out of the dots on the map. But I would say that for most important problems that we're trying to tackle, the more directions we look at that problem, the better off we're going to be. You know, the more ways we evaluate it, the better we're going to understand it so that we can do something about it. And so one of the things that we can do to minimize the subjectivity in that output is use spatial statistics. And so this is the result of a hotspot analysis. It's a technique. It uses a statistic called the Geddes-Ord GI star statistic, which we're going to spend a lot of time talking about exactly how it works in a few minutes. but kind of suspend disbelief there. Here, what we're looking at is the results of that analysis. And you might be thinking, well, how is this any less subjective? There's still red on the map. There's still bloom on the map. I mean, really, this seems just as subjective as any other thematic map that I might make. But it's not. It's a little bit different. And the reason is because what's red on the map are statistically significant hotspots. So they're statistically significant clusters of high numbers of stop and frisks. So it's where a high number of stop and frisks in one of those census tracts is surrounded by other census tracts with high numbers of stop and frisks. And the blue areas are places where you've got low numbers of stop and frisks surrounded by other areas with low numbers of stop and frisks. Okay, so what do we mean when we talk about statistically significant in this context? Well, it comes back to inferential statistics and our hypothesis. Our null hypothesis in the case of spatial statistics is often something that we call complete spatial randomness. So very often in spatial statistics, when we are kind of getting into inferential statistics, what we are comparing against is what would we expect to see in terms of a spatial pattern completely randomly, right? And we are kind of searching to understand if the pattern that we're looking at might be the result of a complete spatial random process. And it's a really important question because if what we're seeing is one version of random and we pour resources into clusters that we see, we really don't expect to get a big return on our investment because those clusters were just random. And tomorrow they might be in a different place, right? So it's very valuable for us to understand that these patterns that we're seeing are more than just random clusters. And another reason that this is so important is because the human brain is an incredibly powerful statistical machine. And one of the first things that our brains learn to do is find patterns. I know when I first had my son, I was obsessed with learning about what was going on in his little brain because he couldn't talk to me and he was basically a stranger. And it's like, well, what's going on in there? And I think it's like at 3 months, maybe they start recognizing patterns. And there's these, studies about tiny babies can distinguish between cats and dogs because they start to understand these patterns, right? So the human brain's very good at finding patterns. So good sometimes that we find patterns when there aren't any. We find patterns based on our biases. We find patterns where we expect to find patterns, things that confirm what we already think. And while that's a very useful aspect of the way our brains work, it also can be quite dangerous. We really want to be able to go beyond that visual analysis and confirm that what we're seeing is meaningful. Okay, so we're asking this question, is there a pattern? We're essentially saying, if I picked up all of these numbers and I threw them down, how likely is it that they would all land kind of how they've landed? So in this case, we see all the really high numbers have landed in a cluster, and it's super obvious. It's pretty easy to answer this question. What are the chances that this happened randomly? I mean, it seems pretty unlikely that this happened randomly, but most of the data that we're analyzing, most of the problems that we're trying to solve won't be this obvious, aren't this easy to kind of figure out. And so what we do is we answer this question using z-scores and p-values. So we essentially, what's on the map is based on those z-scores and p-values. So there is a direct relationship between the red on the map and the level of confidence that we have that that cluster that we're seeing is not the result of a random spatial process. So those are the places where we feel the most confident that that pattern is meaningful. So there's, of course, still subjectivity in every analysis, right? We introduce subjectivity at basically every stop along the way. We decide what data to include and what data to exclude. We decide what questions we're going to ask in the first place. There's always going to be subjectivity in our analysis, but being able to minimize it this way and analyze the patterns by asking such an important question about those patterns that we're seeing is very powerful. So we're able to do that minimization. And at the heart of the way that these tools work, at the heart of spatial statistics, is something that I just want to bring up because as a geographer, I feel like it's my duty, which is something, we call it Tobler's law, or it's also known as the first law of geography. And that is that everything is related to everything else, but near things are more related than distant things. So this is, I mean, it seems very basic, but that's kind of how laws work, right? They have to be these almost obvious things that when stated seem obvious, but are incredibly important foundational ideas. And really, it's just saying that near things that are closer together are more related than things that are farther apart. And the way that spatial statistics works is by building on that knowledge that we have, that kind of free information that we get by just understanding spatial relationships that says things that are closer together are more related than things that are farther apart. And that's going to come up a few times throughout the day. So to dig a little bit deeper into how hotspot analysis works and how all of that kind of comes together in an analytical method, I'm going to pass it over to Alberto, who's going to talk about hotspot analysis.
Great. Thank you so much, Lauren. Let me confirm that you can see my screen.
Yes, but it just looks like my screen. So maybe scroll forward so we're sure it's yours.
Let's try that. Do you see a new?
Perfect. Yeah.
Okay, great. Hello, everyone. So let's talk about hotspot analysis. I think it's pretty safe to say that hotspot analysis is one of the most widely used tools in spatial statistics. So it's really important that we talk about the concepts behind the tool. And there's a few different goals for that, right? So we want to make sure that you understand how this tool works behind the scenes so that you can use it effectively and make the most appropriate decisions given your questions. And also so that you can explain how this tool works and defend the results of the tool when someone is making a decision based on the results of the hotspot analyses, right? And then another important point is that it's really important to distinguish this tool, hotspot analyses, from heat maps, given that the two terms are very similar, given that they're talking about temperature and maps. They are common misconceptions that they're the same thing, but a heat map, as Lauren indicated, these are density surfaces. These are talking about choropleth maps and values, raw values. And a hotspot analysis is different. It's talking about a test for spatial randomness. So let's take a look at how that works. And the first example that we're gonna dive into is looking at polygons. And in this example, we're gonna look at polygonal boundaries that could correspond to things like counties or tracts in the United States. And we're gonna call those features. And each of those features in hotspot analysis must have a value. That value could be the count of an incident, for instance, frisks within that tract, or it could be the amount of observed plant species in a particular boundary. Or it could be a rate. It could be, for instance, the amount of frisks per capita. And in any case, we are looking for a value because we are looking for the clustering of high or low values within each of these features. And there has to be some variation of those values. You need to have a variation that you can test. And another term that's important to come to understand is this concept of a neighborhood. Around each of these features, we will evaluate other features around it, typically around it, and those will form a neighborhood around that feature. And all the features and all the neighborhoods together become the study area. And what the tool will ask is it will take the neighborhood and ask, is that neighborhood significantly different from the study area? And if the answer is that, yes, indeed, it is significantly higher, then that feature, which was the basis for that neighborhood, becomes a hotspot. And there's 3 levels of confidence by which we designate it as a hotspot: 90, 95, and 99%. If it is significantly lower, then the tool will designate that feature as a cold spot with the same levels of confidence. But just as importantly, if the neighborhood is not significantly different from the study area, then the feature will be marked as not significant. And then the tool will repeat the sequence that I think we can wrap our brains around, feature by feature, create a neighborhood, compare that neighborhood to the study area, and designate the results until you have your final outputs for your hotspot analysis. So we've been talking about how neighborhoods differ and if they're significantly different from the study area. But how do we know if those things are significantly different? The answer is found in something called the Geddes or GI star statistic. And this workshop is not going to dive into the specific math and statistic gritty details, But suffice it to say that the tool was founded on a well-established method that you can dig into after the workshop. And we do encourage you to look at our documentation, which we spend some time making sure it's thorough, so that if you do want to know those details, we encourage you to do that. But I think we can wrap our brains around the main concepts of the tool so that you can start understanding how this works and why it's valuable. And we've talked about how it works for polygons. Now you see how it works for polygons. Let's talk about how it works for points, which is a bit different, and there's a few additional considerations. To begin with, let's say that you have points which themselves have a value. So in this case, we have restaurants in Washington, DC, and each restaurant has a sales volume value. This would be quite similar to running it with polygons. The result of these analyses would be similar. You would create a neighborhood around each point, and then the sales volume value would be analyzed, and the result would look like this. However, more often than not, points represent incidents. For example, car thefts in Washington, DC, in this case. Those incidents, the feature of interest is just the fact that that incident happened, that point happened in space. And if you recall, we must have a value with some variation. So one option that you have is to aggregate those counts, those incidents, to polygonal boundaries, in this case, tracks. So the optimized hotspot analysis tool or the regular hotspot analysis tool will allow you to aggregate these points to these polygonal boundaries, and it will count how many of these points occurred, and it will use that as the value. So you would pass your tracks as the feature, the count as the value, and then the resulting hotspot analysis would look like this. And in cases like this, when you're aggregating counts, it's also important to understand whether your question relates to raw counts or whether you should in fact be looking at rates. One of the advantages of using administrative boundaries like tracks or counties is that very often you have other demographic data that you can use for your work, right? So you may have the total population per tract or per county, and you could divide the count of those incidents by that population to create a rate, which may be more indicative of whether there is indeed a problem or not, and control for population a little bit more. It's not that running it for counts is inherently wrong, it's just that they're different questions that may be better served by how you prepare your data, right? Now, one of the drawbacks of using administrative boundaries is that very often they're based on population distributions or sometimes even political boundaries or administrative boundaries. And if you're, for instance, if you're working with ecological data, the presence of a plant species is not going to care that someone drew a map with a line somewhere, right? It's just going to spread unless there's some policy decision behind it, right? So really think about which boundaries you're using. And in some cases, these administrative boundaries may not be the best for ecological purposes, for example. So another example of aggregation schemes is the aggregation to a fishnet grid. And this is the way that optimized hotspot analysis does it if you don't provide a boundary, if you don't have administrative boundaries. The points are aggregated to a fishnet grid or a hexagonal grid. And everywhere that the tool finds an incident, it will create a cell, and then it will count how many other incidents are there within that cell. And the resulting hotspot analysis would look a little bit like this. Now, something to consider here is that the tool by default creates cells only where it finds incidents. But if you look at the gaps in this distribution of points, there could be perfectly safe neighborhoods with no car thefts, and yet those are still valuable data points, right? 0 is a valuable data point to consider in your analysis. And by doing it this way, you may be omitting those valuable locations with 0 values from your analysis. So an additional consideration and an option in the tool is to provide a polygonal boundary that gives meaning to zeros. It essentially tells the tool, where is it possible for an incident to occur? And by doing it this way, the tool will create cells in every location within that polygonal boundary. If there are no incidents within those cells, those will be treated as zeros, and those may be conducive to a more appropriate analysis for what you're doing. And very often it's the case that you really want to refine those polygonal boundaries. If you're looking at car thefts, my colleague often cites that she would very likely create a polygonal boundary that just looks at street networks or just really where cars are, so that you're not aggregating to within houses or neighborhoods, right?
I think the important thing to think about here is it's like, if we drop all the places where there's nothing, then we're leaving out valid zeros. If we just included everything within kind of the bounding polygon, we'd add a ton of zeros. And some of those zeros might be like in the middle of a lake or a river where truly a car could never be stolen because there are no cars. And so the key question is like, where is a zero meaningful? Because if you add too many zeros, all those zeros that are truly not part of your the kind of places where that thing might happen, you inflate the whole data set with zeros, your global average goes down, and suddenly even one car theft pops out as a hotspot because, well, the global average is practically zero because you included an ocean in your study area, for instance. So it's really important to think about, and I mean, this is true in so many analyses. It's especially important in spatial analysis to think about where is a zero meaningful and where should I drop those locations and kind of make them null, because there's a big difference between those null and zeros.
Yeah, thank you. So with that polygonal boundary, that's an option that is that will be shown as a parameter, and we'll take a look at how that works. Another important consideration is that where are the hotspots as a question is very different. It's not necessarily the same as where are the highest values in the data set. If you wanted to find the points or the records with the highest values, you could simply open up the table, sort by your value field, and then simply select the records that have the highest value. Or you could create a choropleth map and provide a symbol to really high values, right? But the tool's question, where are the hotspots, is a test for randomness. And it also works with the concept of a neighborhood. So it's entirely possible that a feature with a low value, even 0, could be a hotspot because we're looking at the neighborhood average rather than the individual feature value. And there's cases when we run the tool and as we're getting started, we would see low values or places that we know are low come back as hotspots, and it's a common learning part of running the tool that you understand that really the object of interest is the neighborhood rather than the individual feature. So these neighborhoods are very important, right? And one more consideration before we show you how the tool works is how do we create neighborhoods and how are those neighborhood sizes determined? And there's a few different methods that you can use to create these neighborhoods. The first method is perhaps the simplest. It's called fixed distance span, and it's the default option used by the optimized hotspot analysis tool. In this case, you pass a distance, and then from the feature of interest, within that distance, all the features that are within that distance will be used as the neighborhood. And the tool will do this feature by feature, creating those neighborhoods using that distance. This can be indeed very appropriate when you have very evenly spaced features or features with the same shape and characteristics like a fishnet grid. But when you have things that are very regular, for instance, counties or tracts that have different shapes based on the population counts there, the same distance could cover a lot of tracts in Manhattan, but could cover very few tracts in the outskirts of Staten Island, for instance. So you have to think a little bit about what neighborhood conceptualization makes sense for you. Another method is called contiguity, and contiguity looks at features that share an edge with your feature of interest. One option is just look at the edges. This is otherwise known as a Rook's case if you fancy yourself some chess. And then a variant of this is called edges corners, otherwise known as Queen's case. And in this case, we're looking not just at edges, but corners as well. Another method is called K nearest neighbors. And in this case, K stands for a number. The number in this example is 4. You're looking at the 4 nearest neighbors to your feature of interest. For this feature, these are the 4 nearest neighbors. For this other feature in a sparser area of this example, even though you would cover a greater distance, those are still your 4 nearest neighbors, and that is your neighborhood. And the same for this other example. And this method is very often more appropriate for cases where the spatial distribution of your points is not random, but you're testing to see if the value is indeed random spatially. And I have a colleague who cites an example that she did where she was looking at the hospitals throughout the United States, and she's trying to test for the cost of the same medical procedure across all hospitals to see if there's some spatial distribution patterns there. And in very dense cities, you may have a lot of hospital options around you. But if you live in a rural, sparse area, even though you would have to have or drive several miles, maybe hundreds of miles to your nearest hospital, those are still the 4 closest hospitals to you. And that neighborhood may still be appropriate. So K-nearest neighbors gives you some options in cases that are where you have very irregular distribution of points or features. Now, the last method that we'll look at for creating neighborhoods, and then we'll show you how the tool works, is called network spatial weights. And this method really works with any network, such as a road network, hydrology network. And it's very conducive for cases where you're looking at transportation cases or social cases where people move along a road network. Humans typically travel in networks. So in this case, you would pass a value. That value can be a distance or time. If we're saying, for instance, look at 15 miles in the periphery of a point, the tool will evaluate along the network, along the road network, for instance, find all the nearby features within 15 miles and deem those the neighborhood. Or you can pass time. You can say, give me all the features within 30 minutes of my feature of interest, and they will deem those the neighborhood. And that can be a really, again, for transportation use cases, hydrology, and a few others, this methodology can be a lot more appropriate. So we've talked a lot about how this tool works, and hopefully you get the main gist of how this works. Now to share with you an example of how to run the tool, I'm gonna hand it off to my colleague, Lynn. And Lynn, I'm gonna share control of my screen. There we go.
All right, hi. So now we have ArcGIS Pro open, and we're going to look at the same data we've been talking about before, Frisk data in New York City. And we'll be using this data to answer the question, where are there clusters of high numbers of people being frisked? This is a question that perhaps a civilian review board, or even the police themselves may ask, in the goal of achieving equitable police operations. Now, as Alberto mentioned, if you have count data, these are just incidents and they don't have a value. So to run the tool, we need to aggregate to some kind of polygon data. To do this, I've aggregated to census tract boundaries, which are an appropriate, like for my case, they're a good option because these are roughly equal in population, meaning there's roughly similar opportunity for someone to be frisked in each track. Before we jump into the tool, if you have ArcGIS Pro open with the project we provided you and you'd like to follow along, then I'd like to take your attention to the Analysis tab, where you can click History to open the History pane. Here, we've already run each of the tools that we'll run today. So if you'd like to follow along, you can double click on any of these entries to open the tool pre-filled with all the parameters. I'm going to open the tool directly from the geoprocessing pane, which I'll access by clicking the Tools button, which opens the pane. From here, I will open the Spatial Statistics toolbox, and in the Mapping Clusters toolset, I'll open the first tool we'll take a look at today, which is Optimize Hotspot Analysis. In the tool, I'll choose the input features as the Frisk layer, which are already aggregated to polygons. However, as Alberto mentioned, you can input points into this tool, and if you do, you'll be able to define bounding polygons where the incidents are possible. However, I've already aggregated these, so I'll choose the polygon layer, and you'll see this, and we'll choose an analysis field as the Frisk count field. And now you'll see that parameters disappeared because we don't need to do any aggregation. Next, I'll run the tool. So as this tool is running, I'll explain its purpose. It uses data-driven defaults to give you a quick hotspot analysis result without worrying about setting parameters.
I'll add though about that quick data-driven defaults. When we were working on this tool, when we were working on this tool, I lost a lot of nights of sleep because on one hand, I didn't want to give good defaults. I wanted people to really think about each one of the parameters that you have to set. Deciding what the conceptualization of spatial relationships is really important. deciding what the distance or the number of neighbors you're going to use is really important. It like sets the tone for what question you're asking. So we did this because we know that we follow a certain set of kind of guidelines as we do this analysis. There's a set of best practices that we could put into place in this tool, but and Lynn's going to say this again, but I think it's worth saying many times, is that we kind of designed this as a starting point. So it's a way of quickly kind of going through those best practices for figuring out, learning about your data, but it is, I would say, never, or very, very rarely never, kind of the end output. It's just a useful starting point. I mean, we literally joked about having it so that when you opened the tool, like one of those pop-ups popped up, said like, I've read and understand all of the things about this, and I kind of agree to be responsible and use these defaults responsibly, because it really is incredibly important to think about these things.
Yeah. And that's what makes it so important to look at the messages. That helps you get deeper into what the tool's actually done. So in the messages, the really important section I think you need to look at is to check the scale of analysis. So like Alberto mentioned, the tool always used the fixed distance band method to define your neighborhood, but it adapts this based on the distribution of your data. So it checks what's the average distance to 30 nearest neighbors in my data set. And for this analysis, it ended up with about 2.5 kilometers of the neighborhood for the neighborhoods. So that's probably what's resulted in these large areas of contiguous hot and cold spots. It's showing us the borough level patterns, but it's not really getting into the neighborhood level patterns. And that's where, for my question, where I want to look at the clusters of high numbers of people being frisked, this result is perhaps too generalized. So now I'll go back to the geoprocessing pane and take a look this time at the fuller version of the tool, the version of the tool that makes you more aware of these caveats and potential pitfalls. And in this version, we'll go through the same steps as before, choosing the frisk layer aggregated to tracts, and the frisk count field is the analysis field. But here I need to consciously make these decisions. So now I have access to several methods of conceptualizations of spatial relationships. And this time I'll choose k nearest neighbors and choose a number of neighbors as 12. So the reason I've changed to k nearest neighbors is because I want to ensure that there's roughly similar people within each neighborhood. And so for this reason, I want to ensure there's roughly similar census tracts in each neighborhood. You can see that the census tracts vary greatly in size. Like over here in Queens, they're quite large. So within our 2.5 kilometer distance band, we may have fewer census tracts than over here in Manhattan, where the census tracts are small. So in the same distance band, we may have many more. You can also consider where there's gaps in census tracts. So here there's the river. So if you were looking at a census tract right on the edge of the river, and you were looking at the fixed distance band, the census tract may have very few neighbors. So you want to think about whether, is it important to include the census tracts across this river or this barrier, or is it not? And think about that when you make these decisions. Back to the tool, I'm also going to check apply false discovery rate correction to be consistent with the previous optimized version of the tool, which does apply false discovery rate correction. The FDR correction adjusts the p-value downwards to account for false positives, and this helps adjust for the spatial dependency and multiple testing problem. And I did actually notice someone had already mentioned this in the chat, so I'm glad you guys were thinking about these problems. This basically gives us a more conservative or a more careful result. So taking a look at the results now, we see these more neighborhood level patterns. Let's zoom in to Queens, where we can look at this small hotspot that's appeared. If I click the Appearance tab, I can use the swipe tool to compare the results from this new hotspot analysis to the earlier results. Previously, we saw there was not a significant hotspot in this area, but now that this hotspot area has popped out, this indicates to me that probably I was right in my intuition that the previous results were more generalized. Using these large neighborhoods was burying or hiding these more neighborhood level patterns. So next, I'm going to pass it back over to Alberto, who's going to introduce you to the second tool.
Great, thank you so much, Lynn. So the next tool that we're going to talk about is called Cluster and Outlier Analysis. And it starts very similarly to hotspot analysis. We have those terms that we now know about, the feature, the neighborhood, and the study area. But if you pay really close attention, look at that neighborhood. We now have the feature and the neighborhood not including that feature. And that's because the tool is going to ask two questions. The first question is this neighborhood significantly different from all other neighborhoods in the study area? Very similar to hotspot analysis. But additionally, we're going to ask, is that feature significantly different from all other features? And that lets the tool create an output that has 4 categories. The first category is high features, or features that are higher than other features, and neighborhoods that are higher than other neighborhoods, high highs. Or its opposite, which is lower features, or features that are lower than other features, and neighborhoods that are lower than other neighborhoods. However, there's these other 2 remaining categories that are really interesting. Features that are higher than other features in neighborhoods that are lower than other neighborhoods. So these are high outliers. Consequently, you also have features that are lower than other features in neighborhoods that are higher than other neighborhoods. So these are low outliers. And when we think about what Lauren mentioned earlier on Tobler's law, that everything is related to everything else, but near things are more related than distant things, these outlier categories almost stand in contrast with that, right? These are likely interesting patterns that you may want to dig into depending on your questions. And this also lets the tool really dig into the feature value if that's what you care about, in addition to the neighborhood value. So to have a look at how this tool works, I'm going to hand it back to Lynn. And let me bring the Pro project back.
All right, great. So we're back in the same Pro project as before. And let me just tidy this up a little bit.
Do you have control?
I don't think so.
Let me provide you control one
Okay.
more time.
My laptop decided it didn't want to play today, so I'm using Alberto's laptop to do the demo. So
Let me
thanks
take you
for your
back to New
patience
York.
here. Yeah, great.
Let me know if you can control.
Yeah, great. Okay, so we'll just tidy up the contents pane a little bit. I always feel like that's a necessary place to start so we can easily see what's going on. And I'll navigate back to the geoprocessing pane. And next, we want to take a look at the tool Alberto mentioned, Cluster and Outlier Analysis tool, which is featured in the same toolbox and toolset as before, the Spatial Stats toolbox and the Mapping Clusters toolset. Now, this tool also has a second version, the Optimized Outlier Analysis tool. That version that is more streamlined, but again, you need to agree to the terms and conditions. So, but for now, we'll jump straight into the Cluster and Outlier Analysis, the full version of the tool. So again, we'll choose the New York Police Department frisks layer aggregated to census tracts, and the input field as the frisk count field. So that our results are comparable, I want to choose exactly the same conceptualization of spatial relationships as 12 nearest neighbors, and I also, for the same reason, want to apply false discovery rate correction. So you'll notice that the tool has an option to apply standardization, and row standardization is automatically applied. What this means is that within each neighborhood, the weights are standardized, and that's particularly important for this data because we've aggregated the data, and that aggregation scheme can cause great variation in values across the study area. You can also adjust the number of permutations. This tool uses a permutation test to calculate the p-values, and increasing the number of permutations can increase the precision of that result. Taking a look at the map, you can see that there are 4 colors on map. The pale pink is a high cluster. This is similar to what you see in the hotspot analysis tool with hotspots. And the pale blue is a low cluster, similar to cold spots. What's really interesting that this tool has been able to identify are the low outliers in dark blue in the middle of high values, and in red, the high outliers in the middle of low values. To gain a better understanding of how these have been computed or identified, we can take a look at the Moran scatter plot that the tools created for us. I'll just increase the size a little bit so you can see better. On the x-axis of this chart is the frisk count variable for every feature in the dataset for each census tract. And on the y-axis is the spatial lag, which is a variable that the tools calculated, which represents the same variable but for each neighborhood. So you can see that where these values are similarly low or where these values are similarly high, these are the clusters. And where these values oppose in this quadrant and this quadrant, these are the outliers. Let's take a look now at one neighborhood over here in Brooklyn, where again, we can use the swipe tool to compare the results to this from this analysis to the hotspot analysis results. You can see that the hotspot analysis showed us that this area was an area of cold spots, and that similarly, most of these census tracts are also low clusters. However, the cluster and outlier analysis result have added more information to these patterns, showing us that though this is an area of low values, it also has some high outliers. Now recall that these are spatial outliers. In the context of the data set, these are not statistical outliers necessarily. They're not necessarily really high and really low across the entire study area. But in this location, these are statistically significant as high values compared to their neighbors. We can use contextual layers to try and gain a deeper understanding of why patterns may be occurring. I'll add a layer on top that represents the New York City subway stations. And you can see that it's interesting that some of these outliers that you're seeing are either coincident with or close to the subway stations. Now, coincidence itself doesn't prove there's a link between subway stations and frisks. However, the tool is a great starting point to help uncover some of these patterns and ask more questions as to whether there may be a link, and if so, why. In this case, I might want to get in touch with community organizations or the police on the ground in this community and help understand if this link is a tangible link and whether there may be a reason that explains this in this neighborhood. So next, I'm going to pass it back over to Lauren, who's going to introduce you to the next topic we'll talk about.
I think I just want to kind of reiterate one of the points that Lynn made about this idea that these aren't necessarily kind of numeric outliers. If we sorted, these wouldn't be the highest and the lowest numbers necessarily. And I love that about this tool because it's just such a clear example of how actually understanding this data spatially and asking these spatial questions about our data really uncovers something that would otherwise be completely lost. Like there's no way to find this in a spreadsheet. You really have to evaluate this in the context of your neighborhood and really taking into account this idea or that the kind of principle that closer things are more related than distant things, because when it doesn't work that way, we really have something to learn there. I often find that finding these kinds of outliers can help us even in our hypothesis generation, right? Like when we go into doing, let's say, a predictive modeling exercise, we have variables that we think are important. Most of the time, the variables that we go into an analysis like that thinking are important are the obvious ones, right? They're the ones that match the general patterns we're used to seeing. But a lot of times finding these spatial outliers, the places where things are different than their neighbors, is a really great clue about variables. What are the characteristics of that neighborhood that it's making it different than all its neighbors? Because that variable may in fact be very important in my model. So I think that understanding these kinds of spatial patterns has a lot of power that maybe we forget about sometimes. Okay, so I'm going to share my screen one last time for this first half of our session to just kind of talk about, can you see my screen?
I can see it, yes.
Okay, great. To kind of talk about where we're going next, which is this idea that, so far we've really talked exclusively about spatial patterns. But I'm sure I'm not telling anyone anything new when I say that a lot of our spatial data is also temporal data, right? I mean, we are increasingly faced with complex spatiotemporal data, and ignoring time in our analysis is really leaving a lot of valuable information about trends and temporal patterns off the table. And so what we're going to talk about next is how we can extend Tobler's law, extend that kind of first law of geography to incorporate time, and what that means in terms of the kinds of questions we can ask and the analysis that we can do. So what we're going to do right now is we're going to take a 5-minute break just to give everybody time to, reheat their coffee or a bio break, whatever you need, and we'll come back at 10:05 to get into space-time pattern mining. All right, we'll give it another 60 seconds. Just things are unpredictable. I really wish we were in person. It would be so great to be in the same room with everybody. It would just be great to be in the same room with somebody. It's been a long 2 years.
Agreed. Definitely missing faces, right?
I know. Yeah. I also just miss strangers. I love strangers becoming not strangers, but soon enough. Okay. All right. Well, let's get started. We do have a lot to cover. Again, I feel like we could talk just about space-time pattern mining for sure a whole day. There is so many little things to think about. So there is a lot to cover. I'm going to share my screen. All right, and here we go. All right, so we're going to talk about the space-time part of the cluster analysis session right now, and we're going to jump right in. Okay, so we're going to talk about a series of tools that are part of a toolbox that is all about space-time pattern mining. And I want to start by kind of thinking about, so we've talked about hotspot analysis, we talked about cluster and outlier analysis, super powerful. And sometimes even when we have temporal data, this is the question we want to answer, right? Like sometimes this is exactly the question we want to answer. So moving into kind of space-time isn't like, well, now all of that's obsolete and all of our analysis should be space-time cubes. I don't think that's the case. I think that there's some really important work being done where just understanding the current spatial patterns is exactly the answer to the question that we're asking. Now, that said, when we do want to think about time, how do we do it? And this is a really important question because like I said earlier, you know, so much of our spatial data is also temporal. So how do we take advantage of that? So we kind of were thinking about this. This was, gosh, now 12 years ago, back in 2010, I was working on my dissertation and we were working on some of these space-time pattern mining tools and trying to figure out how we could go beyond some of our more traditional methods for understanding spatial patterns over time. So one really common way that we might look at time and space together is to look at maps side by side, right? So here we're looking at frists in 2018 and in 2019. Now, just these two maps, these 2 years, I find this pretty overwhelming to figure out, you know, to understand where there might have been change would be very difficult using just a visual analysis of this data. And this is just two maps, right? There's a kind of common problem in cartography, in kind of spatial recognition of patterns that we talk about called small multiples, where you have, you know, what if we wanted to look at 20 years worth of data? Well, we could make 20 maps and try to understand them, but that would really be asking a lot of our brains to do that kind of visual analysis. Now, one of my favorite, with all of the sarcasm I could possibly muster, ways of looking at spatiotemporal data is something like this, an animation, where we flicker a bunch of points on and off over and over again for minutes. And at the end of it, I would argue I know less than I did in the beginning because there's no possible way I can try to interpret this kind of just raw data flashing on the screen. But it's shockingly common to make these kind of animations. Now, animations can be really useful, and we use them as a technique for understanding some of the patterns that we find, but I think that they're probably most useful when we have the opportunity to not just look at raw data flashing on the map, but use it to tell a story, communicate the results of an analysis that boils down some of those patterns that we might see, that might exist in that raw data, into something that's actually interpretable. So the existing methods aren't great. We can do a lot better. So this is kind of a nerdy slide, but one of my favorite things about working at Esri is that on some random Wednesday in the middle of our work week, Waldo Tobler came and gave a talk as part of a brown bag session in our auditorium. And we got the email about a week ahead of time that Tobler was going to be on campus. And I remember emailing my friend Flora, who is the other person in this picture and also the kind of mastermind behind a lot of the slides that you've seen today. And emailing her and saying, we've got to get there early because the auditorium is going to be full and I want to get a good seat. Because I'm a geographer at heart, and it's the first law of geography, it's his law. So it felt like a once in a lifetime opportunity. And we went there early, and of course it was unnecessary. There were people there, but we certainly could have sat wherever we wanted. But we sat there and listened to him give a really interesting talk. And at the end, he took questions. And one of the things I learned in that presentation was, that paper he wrote, it was a paper in 1970 where he said that everything's related to everything else, but near things are more related than distant things. And, he was a young geographer and certainly wasn't assuming that he was writing the first law of geography, right? That would be quite bold, but it did become that. And so I asked him if he knew then what he knew now, which was that it would become the first law of geography, would he change anything? And this was right when I was in the middle of working on my dissertation and we were doing this spatiotemporal analysis. And his response was that everything is related to everything else, but near and recent things are more related than distant things. And it was like a light bulb moment. Also, I wanted to run up and give him a hug because he was extending the law, right? This is an extension of Tobler's law to incorporate time. And what it does is it opens up this world. It opens up all these spatial statistics tools that already kind of work to think about how things are related in space and allows us to bring time into the equation, which is incredibly powerful. And so that's very much the basis of what we're going to talk about in the next couple of minutes in how these tools work. We're really going to see how hotspot analysis and how outlier analysis can be extended to incorporate time and how we've built that out. So when we started working on these tools, one of the first things we realized is that we needed to kind of formalize a data structure. And so we did that in the space-time pattern mining toolbox using this concept of a space-time cube. So when we create a space-time cube, what we're doing is we're thinking about our data not just based on their XY coordinates, but also in bringing in that third dimension that they have, which is time. And you'll see us do this quite a bit throughout the next hour, is using time, that third dimension, in 3D. And so the things at the top of our 3D cube here are the things that happened most recently. And the things that are at the bottom of our cube are the things that are kind of the farthest away in time. And so when we create a space-time cube, this one we're looking at is particularly about aggregating incidents into a cube. You don't have to aggregate. It doesn't only work with incidents. We'll talk about that in a minute. But when we aggregate points into a space-time cube, much like we will have to do for the stop and frisk data, essentially what we're doing is we're creating this data structure, and we're counting in each of the units of that data structure how many points fell within that bin, we call it. And you have options to determine the spatial size of your aggregation, as well as the temporal size of your aggregation. So in this case, we're creating bins that are 10 kilometers by 10 kilometers and that are 1 month. So we know within each 10 kilometer grid, within each month, how many stop and frisks happen. And then by creating this data structure, we have a lot of different ways that we can explore that data. And there's also an important kind of vocabulary that we can use so that we're all talking about the same things at the same time. So the bin is one of those kind of smallest structures within the cube, and it's that piece that has a spatial and a temporal extent. Now, we also sometimes talk about the idea of a location. So it has the same 10 kilometer by 10 kilometer spatial location, but all of those over time represents a location. And really, you can think of that location as a time series, because that particular location has a time series of values that change over time. So you can think of that as, your neighborhood, the COVID cases over time, and that time series. And we can do all sorts of very traditional time series analysis at the level of a location. We also have the concept of a time slice. So what this means is that for any given time period, we can look at what the spatial distribution of values looked like across that whole time period, across our whole study area. And so we're able to take advantage of the bin, the location, and the time slice all together. Now, when we create a cube, if we're aggregating points, we get counts. So we just get the raw number of features that fall within each of those bins. And by default, when you run the tool, we also run a trend analysis. We use a Mann-Kendall statistic to calculate if there is any trend, both location by location. So we can see at each location, has there been a trend? And we also calculate a global trend for the whole study area to see if there's been a trend over time in the data. You also have the option when you're aggregating into the cube to calculate some summary fields. So for instance, if I was looking at 911 calls, I might want to study the spatial patterns of just the raw numbers of 911 calls, or I might also want to calculate something like the average response time per bin to the 911 call. And so we can average, we can sum up a value. It really just depends on what attribute you're looking at, which of these summary statistics is going to make sense. And those can all also get added into your space-time cube. Now, I want to talk for a minute about filling empty bins, because this is really important. It comes back to something we already talked about a little bit in the first session, where we were talking about what does a zero mean? Because when there's an empty bin, we have to decide, is it a zero? Does that make sense? Is that really the value that we want to fill it in with? Now, when you're summing something, or in the case of a count, a zero might make perfect sense, right? And it usually does. If we're counting up stop and frisks and a particular location has had them, if there's a time period where there weren't any, zero is the right number, and we want that zero in our data set. Now, what about if we were doing a summary statistic on the sale price of a home, of all the homes across our study area, and we were aggregating that into a space-time cube? Now, we might have an average sale price of $500,000 and then $550,000 back down to $500,000. And then let's say no house is sold in one of those time periods just by chance. We really wouldn't want a zero there, right? Because it's not like suddenly the average sale price of homes was zero. It's just that we don't have any data in that at that time. And so it might make more sense to fill that empty bin in with spatial neighbors. The value of the average sale prices around that bin may be a better value to put into that empty bin. Or we might fill in with space-time neighbors. Will give us not just our spatial neighbors, but also bring in that temporal data. We might also think about just using the values at that location, but essentially interpolate over time and use just temporal neighbors. Now, this option only makes sense when it's a value that's missing in the middle of your time series. We can't extrapolate the values in this case. We really only want to interpolate. So you can't use this option if you're trying to set a value in an empty bin at the beginning or the end of your space-time cube, but another really valuable option there. Okay, so now I want to talk about some of the ins and outs of aggregating our data in time. Now, in spatial analysis and in geography, when we study geography, we learn about all of these very kind of important things about what it means to aggregate our data and the geographies that we use to analyze our data. So there's something called the modifiable areal unit problem. And essentially what that says, well, it says a lot of things, but the simplest example is that the geography that you use, let's say it's a grid, the size of the grid cells that you use when you aggregate has a huge impact on the results of your analysis. Also, there's, as part of that modifiable areal unit problem, is this idea that you might set a grid here and get a particular result. And then the same exact grid squinched over this way might lead to a different result because the aggregation happens differently. And that aggregation scheme can have a huge impact on the results of your analysis. So we think a lot about that as geographers. turns out that that same problem exists when doing temporal aggregation, and it's actually called the modifiable temporal unit problem. So here we're talking about bringing those both together, and we've got both a modifiable areal unit problem and a temporal unit problem, but burying our head in the sand and pretending that problem doesn't exist does not make it go away, so it's worth talking about. So when we aggregate in time, let's take this data set that we're looking at here. When we aggregate in time, we have to think about a few things. And there's some things really built into the tools that help us think about that. So when we aggregate, first of all, we have to pick a place to start our aggregation. And you have options about this. You can start at the end of your data, the most recent data, and go backwards, or you can start at the beginning of your data and go forward. The default is to start at the end. And that's because what we've found is that most people are more interested in the most recent time period, and they want the time periods before that to inform their knowledge about what's happening now. And so if what we care about most is what's happening now, we start at the end. And the reason that we start at the end is because where you start is the place that's going to have the least opportunity for bias to be introduced. So if you look here, if we have data going backwards and we choose a particular, in this case, a 4-day window to aggregate, it goes back 4 days, each one, but we see at the very end, we only have 2 days worth of data. Our data started in the middle of that last time period. So this first time period, that first bin in our cube, is going to have half of the information that the other ones have, right? And that's not going to be reflective of reality. It's just going to be reflective of when our data started. And so we're going to have this temporal bias kind of built into the aggregation of our data. And when you run the tool, and so if you start at the end, that is in the beginning of your cube. If you start at the beginning, then it will exist at the very top, the most recent, where you're probably the most interested. And so that defaults the end. And what we kind of recommend, and what I use this to think about, is if I see this and the 4-day aggregation window is really important to me, I'm probably just going to chop off that first 2 days of data so that I don't have that bin in my data set. And I just have evenly, I have cubes that evenly break up my data, or bins that evenly break up my data. Or you might rethink what your aggregation unit is so that it becomes something that evenly breaks it up. And we calculate that temporal bias, and that's part of the report, and you'll see that in a minute. So there's also a number of options for how you can aggregate. The default is into a fishnet grid, but you can also aggregate into a hexagon grid. Hexagons have been proven to be quite valuable for ecological use cases that allow for more kind of natural shapes in the patterns of our data. You can also define locations yourself. So you might want to aggregate into polygons that are meaningful, and you can do that. Now, you're not limited to using incident data, right? You can also have data that already exists as a time series. So you might have a feature that has values over time. So you can think of this as like air quality stations that are reporting data at a regular interval, and you might want to create a cube that is truly just those point locations over time, but we put it into this space-time cube structure so that all the other tools can work on it. You might also have, and this is kind of more of a data structure thing, you might have points and then a related table that has the temporal data. Or quite commonly in kind of GIS data, you might actually have those point locations repeated over time. We do that sometimes, even though it's not the kind of, from a data storage perspective, the smartest way to do it, but it can be a useful way to do things like animate things over time, or be able to slice and dice your data more easily in a GIS. So sometimes people share their data that way, but both work. And of course, it doesn't just work with points. A really common use case might be you have, in this case, we were looking at SNAP data, which is the Supplemental Nutrition Assistance Program, or what used to be called food stamps. And that data is collected yearly and at a polygonal level. And so we have polygons that have data over time. And you can think about this as just a time series of polygon data, and you can create a cube that looks like that as well. So lots and lots of options for how you can create your cube. And once you create your cube, then really the fun starts and we get into a lot of really powerful analytical methods. But before we jump into the methods and how hotspot and outlier analysis can be extended here, Alberto is going to show us creating the cube, because it really is, it's one of those things where you've got to start off right and everything else builds off of that. So understanding how to create the cube is super important.
Okay. Let me confirm that you can see my screen.
Yes.
Awesome. So let's create a spacetime cube. And for this example, we're going to stick to the same data set that Lynn was working with in the previous part of the workshop. We're looking at frisks throughout New York City from 2017 through 2020. This time we are going to use the date and time in which each frisk occurred. So we can quickly visualize that as a chart here, looking at the total frisks per month. And in order to create the space-time cube, we're actually going to switch gears from the spatial statistics tools that we were showing earlier in the workshop over to something that we call the space-time pattern mining toolbox. And within that toolbox, you're going to see a few different tool sets. One is about creating space-time cubes, one is about visualizing them, and one is about analyzing them. And then there's a few other interesting things that I encourage you to take a look at if you get a chance. So let's start by creating the spacetime cube, right? So we're going to open up the create spacetime cube by aggregating points tool. To this, we can pass our input features. And in this case, it's all the points. I'm going to hold off on naming the output spacetime cube until we fill in the rest of the parameters. And for the time field, we simply pass the field that contains the date in which each frisk occurred. In this parameter, the time step interval, we make a decision about the size of each of those bins. And you can leave it blank and the tool will try to find a data-driven answer for you. Or if you have some domain expertise, or if you have a very specific question and you have some sense of how large those bins need to be temporally, you can pass that. So for example, we can enter 3 months for the time step intervals. Right here, we have the parameter that establishes whether the bins will be counted from the end time going backwards, as Lauren indicated when she was talking about temporal bias, or alternatively, if we want to count from the beginning going forwards, or even something called reference time, which essentially establishes a tent pole, and then the bins are built from that location or from that time step. We're going to stick to the default event time because we really care about recent incidents more perhaps than the earlier ones. Now we have to make a decision about the spatial dimensions of each of these bins. And by default, you can aggregate to a fishnet grid. But to be consistent with some of the things that we were seeing earlier when Lynn was showing you the hotspot analyses, we're going to use defined locations, and to that pass our tracks as our defined polygon locations. And when you do that, you have to tell the tool what field specifies the ID for each of those locations. And let's go ahead and run the tool. Oh, and actually it reminded me of something important. I didn't name the output spacetime cube, which is by intention. And what I like to do is, now that you've filled in the parameters with the dimensions of each bin, go ahead and name your output spacetime cube with that information, because it's very seldom the case that you'll run a single spacetime cube. You'll create a single spacetime cube and then just analyze that one and then call it a day. You're likely going to create several different spacetime cubes to look at the problem from different angles to try to see if the aggregation units make sense for what you're trying to do. So this happens to be about frisks. I'll go ahead and name that there. These are 3-month bins by tracks spatially. And I think now we're ready to create our spacetime cube. Now, behind the scenes, the tool is creating something called a netcdf file. We call it a spacetime cube, but essentially it's creating that structure that Lauren described in the slides. And the tool doesn't provide you an output layer automatically. It almost looks anticlimactic, but it's doing a lot behind the scenes. And the main thing that I would suggest when you run this tool is to look at the geoprocessing messages by clicking view details. That gives you some information about the spacetime cube that you just created. For example, at the top, you'll see some warnings, most likely. And those warnings relate to, for example, features that could not be aggregated into the defined polygon locations. Very often, those are the cases where points were right on the periphery of your tracks, or perhaps there are indeed polygons that don't cover the entire extent of your data. So maybe that's something that you need to take a look at and fix. And that gives you a sense of how many of those features had that problem. Additionally, you get messages. Here you get the characteristics of the output spacetime cube with the start and end, and how many time steps 3-month bins resulted in. These are things that we likely know because we were specific with entering the parameters. But if you left this parameter blank, this would be the place where you would see what the tool determined was an appropriate time step interval for your data. And that's where you could make some decisions about creating a different spacetime cube, depending on this value. You also get a sense of the temporal bias. Back to Lauren's comments about temporal bias. If you happen to have some, this would be where we would inform you of that. And it happens in the first time step because we started counting from the end, going backwards 3-month steps. Additionally, you also get information about the overall data trend for this spacetime cube. And this would give you a sense of whether that trend is significant and the diagnostics that we use to make that assessment. So you could get some additional information there. So we've created the spacetime cube. Let's go ahead and visualize it so that we can really see that data structure. I'm going to go back to our geoprocessing pane, and I'm going to open up the spacetime cube visualization toolset and open up the Visualize Spacetime Cube in 3D tool. And
I'll also just note, it's worth noting that we're showing you where the tools exist in the toolboxes, because I personally think it's really useful to see them where they live, because most of the time they live near other things that maybe you didn't know about, and it's kind of a nice way to discover new things. But of course you can search for these tools, so you don't have to remember where the tools are. Eventually you'll just end up searching for them.
Yeah, you can enter the name up here and find it, but I also still prefer just to go through the hierarchy of toolboxes and tool sets. It's nicely organized in there. So yeah, let's go ahead and open up this tool. And as the name implies, we're going to visualize the spacetime cube that we just created. So we're going to look at the folder in which we created this, pass our input spacetime cube. It's a .nc file. And there are 2 parameters to fill in. One is your cube variable. We've counted how many frisks happen on a 3-month by tracked bin. So that's the only variable that we can use. However, actually back to the tool, I failed to talk about something that you can actually do when you're aggregating. You can use a summary field, and this is where you could specify that if your input data has a value of interest, let's say that you're concerned with the duration of the frisks, you could pass in that field, the duration minutes, and then fill in a statistic such as the mean for the bin. And that could become an important analysis question, right? If you're looking at a difference or you're testing for randomness and the distribution of duration of risks. And that would be available, therefore, in the Visualize Spacetime Cube in 3D tool under the cube variable. So let me go ahead and pass my input spacetime cube once more, pass my count. The second parameter that you would have to fill in is called the display theme. Right now, the spacetime cube only has the values, meaning the count of frisks, bin by bin. So we're going to specify that. Later on, once we start analyzing and appending results of analyses to the spacetime cube, you'll see those in the display theme option as well. So this is a tool that you often will come back to as you run analyses on the spacetime cube. So here's the result of visualizing the spacetime cube. I'm going to tilt this a little bit so we can see the 3-dimensional structure. And if we zoom into Southern Brooklyn to Coney Island, we can see that each column essentially corresponds to the tract. We're showing essentially points at the centroid of each tract. And the lower parts of that column correspond to the earliest time steps. The highest points in that column correspond to the latest time steps. And then the color of the bin corresponds to the count of frisks found in that bin. In essence, this is essentially a choropleth map of your spacetime cube, but it starts to give you some sense of the distribution of those frisks, not only spatially, but also temporally now. So I think it helps to explain how these methods work and set you up nicely for what Lynn is about to talk about now. So I'm going to hand it back to Lynn. And Lynn, I'm going to share control with you.
All right. So Alberto's shown you that the spacetime cube is a powerful visualization tool. But of course, it's not just about visualization. We created the spacetime cube so that you can apply many analysis techniques to your spatiotemporal data. And the first of these is emerging hotspot analysis, which identifies trends in the clustering of counts or summary fields in a spacetime cube. This description might be a little bit familiar because it builds on the methods of the hotspot analysis tool you learned about before the break by extending the concept of what it means to be a neighbor, including not only what is near in space, but also what is recent in time. So let's take a look at how this works. So within the space-time cube, each bin is evaluated in the context of its neighboring bins, which includes the spatial neighbors, the green ones, the ones that are close geographically, and also the temporal neighbors, the ones that are closest in time. So only bins that are proximate in space and close in time are considered related. Each bin's neighborhood is defined and then compared to the study area to ask, is this significantly different from the entire study area? This global window, in this case the study area, that we compare to, is called the entire cube. But this can be modified in the tool. In deciding what method you choose, entire cube or the next method I'll show you, it's important to consider what you're comparing the neighborhood to. If you compare the neighborhood shown in green to the entire cube, you need to consider, is the global average of the space-time cube meaningful? If there's an upwards or downward trend in the cube, or the range of values in the cube is high, you need to take caution with this comparison because it will change the definition of what it means to be a hot or a cold spot. For example, if there are low values at the start of the time series, but the trend is upwards, so there are high values at the end, you raise the bar for what it means to be a cold spot at the end. So if any of these concerns are true for your analysis, you can set the global window parameter to instead use the neighborhood time step, where the bin's neighborhood is compared to each spatial location in the neighborhood time span only. So the global window is only locations that are near in time, making the issue of trends impacting results less apparent. So once we've evaluated this comparison between the neighborhood and the study area, if the neighborhood value is significantly higher than the study area, then that bin is marked as a hotspot. Just like in a two-dimensional hotspot analysis, each bin is assigned as a hotspot, cold spot, or not significant. As you learned before, these hotspots and cold spots are probabilities of how likely it is that each bin belongs to a non-random cluster of both high or low values. The type and intensity of clustering is then summarized for each location and categorized based on the location's pattern or trend in clustering over time. There are 16 possible types of significance, and also at the bottom there's no pattern detected. So there's 8 categories for hotspots and 8 for cold spots, each describing a unique temporal pattern. For example, this location has been marked as a sporadic hotspot, meaning that most recently it was hot, but over time it has switched back and forth between hot and not significant. This location is marked as an intensifying hotspot, meaning that it has been hot for at least 90% of the time, and that there is a significant upward trend detected in the clustering intensity. This hotspot has been getting hotter. Finally, in this location, it's marked as a new hotspot, meaning that it had never been hot before until the most recent time period where it became hot for the first time. Now, all these 8 categories, like new, sporadic, intensifying, are the same descriptions, but for cold spots. So now I'm going to pass it over to Alberto, who's going to show you a demo of the tool in action.
Great, thank you. So we have the space-time cube that we created in the previous demonstration. Let's analyze it. We're gonna stay here in this 3D visualization, but in the geoprocessing pane, we could search for the tool, or we could simply go down to the next tool set under space-time pattern analysis, and we'll find the tool called emerging hotspot analysis there. Now, with this tool, we'll pass the input spacetime cube that you created when you ran the create spacetime cube by aggregating points tool. Here's our file. The analysis variable is the count of risks. That's the only analysis variable that we can calculate it when creating the spacetime cube. If you had the average duration, that's an option that you could pass there. And then we're going to have to make some decisions about the neighborhood, and not just spatially, but temporally. So first, let's think about spatially. We can say that there's a fixed distance around each bin, and then pass the neighborhood distance. Alternatively, to be consistent with some of the results of the hotspot analysis that Lynn showed in the beginning of the workshop, we're going to change this to k nearest neighbors and look at 12 nearby bins spatially. But now we also have to define the temporal dimensions of each neighborhood. In this case, these are time steps that are added to each feature's temporal dimension. So if each bin is 3 months, if we add 1 neighborhood time step, we're looking at an entire neighborhood of 6 months. If you think about New York City and frisks, over the span of a year, you have the summer when a lot of people are out and walking around, and there's perhaps more activity and more chances to perhaps be frisked. But then you may also have colder months in the winter when activity lowers and perhaps there's lower chances to frisk. I want neighborhoods to incorporate the entire year. So in order to do that for this first pass, at least, I'm going to say 3 neighborhood time steps, meaning that we're adding 3 sets of 3 months. And now that establishes the dimensions of your neighborhood. You need something to compare that neighborhood to, whether that's the entire cube as set by default, or the neighborhood time step. And in this case, I do want to compare it to the neighborhood time step. If you looked at the chart earlier of all the New York City frisks, in the later time steps, there does seem to be some pattern as soon as the pandemic started where frisks lowered. So I want the comparisons to be in the context of the year by which each neighborhood is being compared. So let's go back to our tool and to our scene and run it with neighborhood time step. Now, while the tool runs, I want to take a quick side note. If you're ever curious about all of these settings, it's very likely that all of this information is not going to be fully remembered, no matter how hard we try. There's this question mark button at the top right of all of these tools, and you can click it and it'll take you to the tool documentation where you can see examples and see all the parameters in greater detail. Okay, so we've run the analysis. Let me go ahead and put it in our 2D layers and let's take a look at these results. So I want to compare it first and foremost with our 2D results. So I'm going to drag and drop this scene here. And on our 2D map, let's bring the hotspot analysis results that Lynn showed earlier. So right off the bat, we see similar patterns in terms of hotspots and cold spots, right? The areas in the Bronx, the northern part of Manhattan, and parts of Brooklyn stand out as hotspots when we run emerging hotspot analysis as well. However, there's additional detail because of these categories that Lynn described. So let's zoom into one such category, or one such neighborhood rather. We're going to go over to Brooklyn. And let me pan a little bit to the north, pardon me. Let's give the tool just a moment to finish rendering here.
Or for Murphy's Law to really nail us. Yeah, there you go. Perfect.
Let's give it just a moment. I may be beating up my laptop a little bit too much this morning. And I think what we can do is very quickly restart this project. Yeah, let's do that.
It's fine. Happens. At least you know this is really happening live, guys.
And the project is coming right back up. So thankfully we have a backup restored, hopefully with the results of our emerging hotspot analysis. And if not, we can quickly create them. So let's take a look at that scene again. So in essence, what we're going to look at is the results of emerging hotspot analysis. We're going to zoom into Brooklyn. And what I'm really curious about is for those categories, and let me bring those results one more time. I think we can just run it one more time really fast. I think repetition is not necessarily bad. We have our input spacetime cube. And let's let the tool load here. And that'll give you a chance to see all the parameters yet again. There we go. Let's fill in our variables. K nearest neighbors, 12 neighbors. And then set our time steps to be 3 and compare it to the neighborhood time step. There we go. All right, let's get our results back. And then let's zoom into all of New York City. And then zoom just to Brooklyn. And the map is loading. So here we'll have the results momentarily. So what we care about in the context of a hotspot, there's these categories, right? And Lynn explained a few different options. There's new hotspots, consecutive hotspots, intensifying hotspots, persistent hotspots, and so on. And what we'll see in this neighborhood once this loads is that there's a few locations that are sporadic hotspots, and then a few locations that are new hotspots. So let's give the map a moment to render here. There we go. And actually, I need to put this in the 2D layers section. There we go. That should render it a bit faster. So I think it's mostly my fault. I wasn't putting it in the right location. There we go. So we have these tracks that were categorized as new hotspots, and then we have these other tracks that were categorized as sporadic hotspots. And to really dig into what that means, what does it mean to be a sporadic hotspot for these tracks? Something that you would likely want to do is go back to the Visualize Spacetime Cube in 3D tool. But now that you've appended the results of emerging hotspot analysis to your spacetime cube, you can use that as your display theme. So here, previously you only had value because we hadn't done the analysis yet. Now you have hot and cold spot results. So let's go ahead and run that. And once this is done, what you'll get is that 3D visualization of the spacetime cube with the raw outputs of the GEDIS or GI star statistic for each bin, in addition to that category in 2D, to those categories in 2 dimensions. So here it's about to visualize them. There we go. So zooming in a little bit to this region, the new hotspots are fairly straightforward to understand. These are locations where you had mostly not significant bins all the way until the last bin, and suddenly it became statistically significant. Those could be very important if you care about places that now are important in terms of risks and you want to see recent activity. But the sporadic hotspots near it, I think, are quite interesting, especially when you combine these 2 layers, right? The 3D and the 2D layer. You could see some oscillating patterns where perhaps in the winter you could have lower activity, but in the summer you have higher frisk activity, and then back to the winter you have lower activity, and so on. That gives you some indication. If your analysis is more about explaining what seems to be associated, or trying to dig into what seems to be associated with frisks, this could be a useful start. One more tip is in the result of the emerging hotspot analysis tool. If you're ever curious about these categories and what they mean, you actually see all the categories explained in the messages of the emerging hotspot analysis tool, and all the definitions are available there if you ever need to really dig into what exactly does diminishing mean or oscillating mean compared to sporadic. So
will you zoom out a little bit, Alberto?
Yes.
So I think it's just worth kind of noting when we first were working on designing this approach, this was going to be the output, right? It was going to be this beautiful space-time cube with the results of the statistic, right? We can see the hot spots, we can see the cold spots. And it wasn't until we started trying to use it that we realized this is way more information. Even though this is the result of doing an analysis, this is still way too much information for us to try to make sense of, right? Like there are so many bins here, and this isn't even a very large cube. I mean, sometimes we're doing global spatiotemporal analysis and we're just trying to make sense of so much data. And so the way that I like to think about it is it's like that 2D map the kind of default output with the categories is our attempt at kind of boiling down those patterns into something that we can investigate. And so as an analyst, I like to think about it, or a data scientist, I like to think about it as I need both, right? So this one, the kind of boiled down version, helps me pinpoint where I might want to investigate further, but it's definitely not enough. So for instance, we don't really see any here, but there's another kind of category called an oscillating hotspot, or there's a couple. And an oscillating hotspot means it's hot at the end, but it's been both hot and cold. Now that could mean very different things without investigating further. So sometimes you dig into an oscillating hotspot and you see that it started cold, then went to not significant and ended hot. Sometimes an oscillating hotspot is cold, then hot, then cold, then hot. And those are two very different temporal patterns that I would want to understand before I decide, okay, well, actually, yes, this is a place I do want to investigate further, or I want to understand why I'm seeing the flip-flopping versus the shift from cold to hot. Like those would be two very different patterns. And so it's important to be able to kind of play around with both of these as the person kind of trying to make sense of the results, so that we can then take what we learn from bringing all of this information together and help communicate it to the folks that probably aren't going to want to dig in and look in depth at all of this, but we figure out what the key patterns are to point out and then share that with decision makers, with the public, for instance. So just kind of a way of thinking about how we bring together that 2D kind of boiled down patterns, those categories, and the statistical results. The other thing worth mentioning is that those categories, those aren't set in stone, right? Those are what we decided were going to be particularly useful patterns worth mentioning, but they're not. The true kind of statistical result is that space-time cube. And so if you want to kind of say, you know, I think that the difference between intensifying, persistent, and diminishing, which all require that you're at least 90% of the time significant, if you don't care so much about the z-scores going up or down, you could say, I'm just going to call them all persistent because that's all I really care about. There's nothing kind of quantitatively wrong with coming up with your own categories based off of the output of that hotspot analysis. We just thought that these were useful and default to them. So I think that that's another thing that's really important to understand about the results of the analysis.
Great. So now with these results, we're going to take a look at one more tool within the space-time pattern mining toolbox. And for that, I'm going to hand it back to Lynn.
All right, great. So local outlier analysis is a second tool that you can apply to the space-time cube to identify statistically significant clusters and outliers in the context of both space and time. This extends two concepts that you learned today: the concepts behind the cluster and outlier analysis tool that we talked about before the break, and it also extends the concepts behind the emerging hotspot analysis, borrowing the same spatio-temporal conceptualization of what it means to be a neighbor. So just like in an emerging hotspot analysis, a bin's neighborhood is defined in terms of spatial and temporal proximity. But in a local outlier analysis, the bin itself is not included in its own neighborhood. This allows us to make a different type of comparison. Instead asking, where is the bin significantly different from the study area, and where is the neighborhood significantly different from the study area, to identify the value clusters and local outliers. The result includes 4 possible types of significance, which should be familiar from before. There's 2 types of clustering: a high value with a neighborhood with a high value, and a low value with a neighborhood with a low value. And there are 2 types of outliers: the bin with the high value surrounded by a neighborhood with a low value, and the opposite, the bin with a low value surrounded by a neighborhood with a high value. Like for emerging hotspot analysis, these temporal patterns can be summarized into a single result for each location in the space-time cube, to try and do what Lauren was talking about, kind of condense all this confusing, sometimes, information into a single 2D result. The two-dimensional output tells us if a location has ever been significant, and if so, which type. For example, this location has been marked as only high cluster because over time it has been significant, but only as a high cluster. But this second location has been marked as the multiple types because over time it has flipped between a high-low outlier and a low cluster. So again, I'm going to pass it back over to Alberto, who's going to show you the tool in ArcGIS Pro.
All right. So let's run a local outlier analysis. And for that, you actually find it right next to emerging hotspot analysis within the spacetime pattern analysis toolset, or you can search for it like before. For local outlier analysis, you'll find that the parameters are really similar to emerging hotspot analysis. So if you start to get used to that tool, it's very easy to run this tool as well. Let's pass our input spacetime cube that we created earlier, the analysis variable being the count of risks. And to be consistent with all of the previous demonstrations, we'll use the same conceptualization of spatial relationships. That means 12 tracks near each feature and 3 neighborhood time steps, which makes it 1 year. Now we have this parameter for number of permutations. We'll leave it at the default setting, but a best practice is that once you've experimented a few times, it's a good idea to increase the value here to get more consistent results across multiple runs. That does increase the duration of the tool, but that would be a consideration. Maybe in the beginning, you leave it at the default and then change it as you get more comfortable with the data set and the question. And then we'll change the global window to be neighborhood time step as well and run the tool. And like before, the results are summarized in 2 dimensions, the way that Lynn showed with the 6 categories. And we'll take a look at that in 2 dimensions, but I've also taken the liberty of already running the visualize spacetime cube in 3D tool with the local outlier analysis results so that we can really dig into some locations. So first, let's take a look at this 2D layer. A lot of the locations come back in purple, meaning that they had multiple types at that location. And we'll really need to dig into 3 dimensions for that. So let's go over to that scene. It starts to become a little bit of muscle memory that you'll run the emerging hotspot analysis tool or local outlier analysis tool, and then go immediately to visualize spacetime cube in 3D to start to interpret. So for those locations that are shown as multiple types, you can look at it in 3 dimensions to see what are the characteristics that make them multiple types. For this area in the south of Brooklyn, these are generally cold features in cold neighborhoods, but at some points they are high outliers within those cold neighborhoods. So even areas that may not be particularly of concern, they could, if you dig in deep enough, looking at the 3D outputs, they could have additional characteristics that could help you find other details in the analysis, right? And that stands in conjunction with what Lynn was showing in the earlier demonstrations. So that's a brief look at local outlier analysis. You would run local outlier analysis and then visualize spacetime cube in 3D to get this output. And it's very often helpful to compare both of the results together. Now I'm going to hand it back to Lauren, who is going to talk about how we share some of these results with people that need to consume the results.
Yeah, so kind of a insider speak here, but when we were building these tools originally, and I first showed the results, those 16 categories for emerging hotspot analysis to my own leadership, the response was, that's too many categories. I don't like this. And, you know, I think they've come around to valuing the 16 categories on one hand, but on the other hand, they were right? Because for them, for the decision makers, for the kind of executive level folks who are trying to make sense of the results of this analysis, they may very well not need 16 categories. I, as the scientist trying to understand the patterns, frankly, I would take 32 categories if that was an option. Like, break it down to as fine grained as you can to help me understand these patterns so that I can then tell a story of the results of the analysis. And so it's really important to kind of think about, you know, I know we're talking about analytics and we're talking about methodology, and that is certainly the thing that gets me the most excited, but we really also have to think about how we tell that story. It is the difference between our analysis making a difference and it not making a difference. And, you know, there's this explosion in the importance of data science, the importance of, I mean, whatever we call it, like people understand the value of analysis more now than ever. And that's awesome. But it also means that decision makers have a lot of information products being put in their face, right? And they are trying to make sense of all of these different information products to make a decision. And as much as we would love for the only consideration to be the rigor and validity of the analysis of the analyses being shown to them for how they're going to decide what to use and what not to use, we know that that's not the case, right? I mean, to be fair, they don't most of the time even have the necessary knowledge to make that call, right? And so we are competing in a lot of cases with information products that are beautiful but pretty shallow, right? And so if we want our deep, sophisticated, incredibly valid analysis to kind of impact the decisions getting made, we have to compete in that space of creating visual, beautiful, compelling, approachable information products. I've been reading a bunch of things lately about the importance of scientific communication, and I'm sure some of you have seen some of these discussions that have gone on about the role that scientific communication had to play in that recent movie, Don't Look Up, where, you know, the world's falling apart, literally about to get blown up, and we're using big words and jargon to try to help people understand how important this is, but we're not helping them understand because they don't know what they don't speak the same language. And so really the importance of being able to effectively communicate great scientific research is critical. And so this is an example that I worked on with some folks at World Resources Institute. This is a project called Global Forest Watch, and we're looking at deforestation and using emerging hotspot analysis to look at forest loss in a couple of key areas. And this is a story map that they created to kind of tell this story. And so in going through, they set some context, understanding what the problem is, what the analysis is about, why it's important. Also getting into some explanation of how it works, how the method works. And then they really thought about, how do I effectively communicate the results of this analysis? How do I simplify those categories to mean something to the policymaker who's going to be looking at this story map? And so what they did was all sorts of things, changing symbology. You'll notice here they're using gold to show persistent hotspots, because that's what they thought would resonate most with their policymakers. You'll also notice there's no cold spots here because they didn't think it was important for the policymakers to look at cold spots. They're just not relevant to the questions that they're asking and how they're going to apply policies. And they also chose to kind of display the information in a way that builds. So you're not just throwing all the information on at once, you're helping the person kind of walk along and understand what all of these results mean piece by piece. This progressive disclosure can be an effective kind of communication style. So all sorts of things that they're kind of changing, bringing in contextual layers to help understand how these deforestation hotspots overlap with where the forests are. Is also a key kind of piece of their analysis. And so they did this storytelling, I think, really effectively. I've also worked with sales organizations who are using emerging hotspot analysis to look at sales. And when they go to talk to a decision maker, they can't show high sales as hotspots because for their decision makers, a hotspot seems like a problem area, but high sales are not problem areas. It's the low sales that are problem areas. And so I've seen them flip the color ramp so that suddenly the low values are red and the high values are blue. And there's nothing wrong with that. It's just what most effectively communicates to the people that are kind of using the results of your analysis. And so I think that it's a really important, I think we should constantly be thinking about how we are communicating the results of our analysis. We think about it a lot when we're building tools. And I think as researchers, as folks doing this kind of work, it's incredibly important for us to be thinking that way as well. And we're going to talk a lot about that 2 weeks from now in the workshop on story maps. I'm super excited about that. We partnered with our story maps team. And I think that, I'm biased. Obviously, I think the analytical tools we've been building are the most important thing going on, but I think that the work that the Story Maps team has been doing to help communicate the results of our analysis is pretty critical too. So just some kind of housekeeping things. Stick around. We're here for the next hour to kind of answer your questions. You can try out some workflows while we're here, and if you run into something, ask us some questions. We can kind of use the chat to do that. And if we'll kind of go through those questions for ones where we think it makes sense to talk amongst everybody, we can do that. And if there's a really specific question that you've got, or you want someone to really see what you're working on, we can also set up some breakout rooms. We've got 6 additional folks from our spatial stats team that are on the line who are ready to answer your questions and go into those breakout rooms. So we're excited about that. Next Friday is the session on machine learning based cluster analysis, which we're really excited about. And then the following one is the story maps one. I'll also direct you to our resources page. If you go to esriurl.com/spatial-stats, you'll find workshops similar to the one we showed today, as well as others that we haven't had a chance to cover. We've got some kind of spatial modeling and prediction tools that we build that are also explained there, some kind of simpler but also really powerful kind of tools to measure geographic distributions that we talk about there. There's also a lot of resources shared there. So tutorials, hands-on, what we call learn lessons, where you can download the data and walk through an analysis. Because I know for myself, at least, the best way to learn is just to do it. And so those learn lessons can be really helpful. And also just today, the learn lesson on those police stop and frisks was released. So if you go to esriurl.com/police stops, it'll bring you right to that learn lesson that Lynn and Alberto have been working on for at least, I think, at least a year. But that's a really, I don't know, it's something that we're really proud of, and that goes through a number of different cities and looks at those examines kind of racial inequities in those police stops from a lot of different angles. And I think it will be a really useful learn lesson for you to dig in deeper if that's first of all, to learn a bunch of new techniques. Also, if that's an issue that is something that you're passionate about, as we are, those kinds of being able to use spatial analysis to address things like racial equity is something that I know our whole team is really passionate about. So we're excited to be part of that work, which was also done in conjunction with our racial equity task force at Esri, who is dedicated pretty much full time to doing work in that space. So it's been a really fruitful collaboration, and hopefully just the beginning of a lot more opportunities to do that kind of work. So it's office hours, and we're really grateful that so many of you stuck around for what we know is a pretty long session. And I also know school just started again, and so you're all being bombarded with a lot of opportunities for learning. So we're just really grateful to have gotten the chance to share this with you today, and hopefully it is just the beginning.